Welcome everybody to this webinar about predicting power usage and duration of thermal treatment. I have my co-authors listed here. Thank you to all of them for helping preparing for this. So I will get into it. We predict treatment, thermal treatment, and how much power and energy we need because it is very, very important, of course, for those who pay for the treatment. Just a little reminder of what our product is. In situ thermal treatment. On the left side at the top, you see a typical ISTD in situ thermal desorption project with heaters going down in the ground through vertical casings, heating up everything in between them. And on the right side, you see some of the process gear sometimes used. This was a very complex site that had both steam injection, so you see a boiler that says wear on the side that makes steam that goes in the ground. And in front, you see a thermal oxidizer with an acid gas scrubber and a blower package and other things. So we have some pretty heavy equipment involved, and it really is important to know how long this equipment has to be out there so we can make the agreements and estimate the price of it. Down at the bottom is what we're really after, getting out of the ground, LNAPL, DNAPL, nasty stuff from different chemical spill sites. Another reason why it really matters is sometimes we treat all the way up to houses. And again, here you see some heaters sitting within probably 3-4 meters of a house with insulation board between the vapor cover and the house. And in this instance, we had to negotiate agreements with the owners of the house to not be there for the duration. And of course, they were very interested in knowing how long it was going to take and before they could move back. In terms of expenditure over time, a thermal project, typically the operational period is somewhere between 3 and 12 months depending on the site, the size. And as you can see here, the operational cost could be 30% of the total cost or maybe 50% of the total cost for a project that runs long. And on the x-axis you can see once we get into operation, if we have a large uncertainty as to how long it's going to take, then that translates into a pretty decent change in price or cost. So we could have 10–20% of the total project cost be somewhat uncertain if we don't know how long it's going to take until we have heated the site, extracted the mass, and achieved the remediation goals to allow us to start cooling the site off. So another incentive really to be as accurate as we possibly can is that. So what's the first step for us to be reasonably precise with the predictions? That is to understand the site properly. The conceptual design model is typically what's used, and CSM as an abbreviation. So we need to understand your site based on all your knowledge so that we can basically design the surgery, if you will, for it. And it starts with understanding the soil types on the left, having data from drill logs, from soil cores, to know where the chemicals are and in what geology they are. That's super important. On the right side in the upper, we need to have something similar to this, which is a conceptual site model or a cross-section for one of our sites that reveal to us, and like in this case, at a low point in an upper sandy zone where NAPL, DNAPL had actually been spilled and gone down, and then gone down to a more permeable layer down below a clay interface and spread across there. You see those blue little profiles, blue lines in the CPT logs there. That's the MIP response, membrane interface response, and that's TCE that actually spread across a layer. So for us to design a good heating strategy and a good vapor extraction strategy for this and to get the duration reasonably close, we needed to first understand this spreading pattern. Then we needed to design our heaters and our vapor and liquid extraction system to pull the mass out from the right depths So it's crucially important to understand how the chemicals were released, how they spread, so we can basically make them come back out as well. The next picture down shows a model of how steam may progress from 2 injection screens over time. Again, if we're using steam, it's super important to understand the permeability in all directions in the zones where you're injecting the steam, so you can predict the heater, the heating rate, the well spacing, and where to place your screens, how long the screen should be, so that you can get the near uniform heating you see here on the right, most of those little transects. Down at the bottom is just an example from a steam site, Guadalupe oil dunes, where the steam would migrate down at about 50-foot depth, and the target was to keep it down there for an LNAPL site. But it's just to illustrate how it can be very different from site to site. So it starts with the conceptual site model. We really need to understand that so that we can pick the right thermal technology and know how to capture everything that is mobilized, vaporized, and to be extracted. So here you see just an illustration of the 3 dominant thermal technologies being used: steam-enhanced extraction, SEE, in situ thermal desorption, ISTD, electrical resistance heating, or ERH. And what I'm kind of trying to show there is that they're all different and they have overlaps, and some sites all 3 methods will work, some sites only one of them will work. And again, the point is understand the conceptual site model and have that determine what heating technology or technologies, if you combine more than one, is the best fit for any particular site. Once you do that and you pick the right method, then you are in a much better position to predict how long it's going to take and the energy demand. Down at the bottom is an illustration of how important it can be to understand the groundwater flow. This is from one of our sites where we had to build a custom model to predict not just how the target treatment zone heated up, which is where you have that kind of dark red shading, but also what thermal impacts would be down gradient when groundwater was moving from left to right in the alluvium there. And that was done so we could predict temperatures down gradient, and that has effects for enhancing natural attenuation reactions, but it also has potential effects for making it too hot for PVC wells to be functional in the down gradient direction. So in this case, it had 2 purposes: to study the time it takes for some of the water to go down gradient and heat up, and then which PVC wells had to be abandoned before thermal treatment so that they weren't there and to be damaged during this. Once we have the good understanding, we build these numerical models, and I'm just showing some example output. Of course, one of the key things we need to know in the upper left is what are the temperatures we're going to reach down the hole or subsurface. And these are typical temperatures showing that you heat for about, say, 60 to 80 days, and in your target depth, you want to reach boiling temperatures at that if you're treating for VOCs. And then you sit there for a while. It's not just go up to the temperature, but you also have to remediate, and that is to boil water for a while until you have low enough concentrations that you can stop. And this is one example of a project where we predicted about 160 days of heating. And then you turn the heat off, and you can see the cool down starting with the curves going down. To the upper right, there's the associated energy demand that we need. The red curve shows the cumulative energy, or megawatt hours, to be actually kilowatt hours here to be used, and our prediction for that, of course, depends strongly on the duration and on the intensity of heating. And the other curves are just simply some of the energy flows. Water, energy in the water being extracted, energy in the steam being extracted, and heat losses. So that energy balance is key, and I'll get more into that in a little bit. The lower left, where it says heat spreading down gradient, is one of the outputs from the model I showed in the previous slide, showing that the temperature over time during cool-off, after heating. The upper line is when we have the whole treatment zone at boiling, and then we let 15 days go and you see how we predict a lower temperature. And as time goes by, the treatment zone cools off and some of the heat moves down gradient in this case, which was also something that creates a beneficial condition. Down gradient, you can see how we're in the range of 20 to 30 Celsius, quite a bit, and that's where the thermally enhanced anaerobic dechlorination is best. So just one way of using that model. The lower right is an example from a site in Australia, and where we are simulating basically heat moving outside the treatment zone, and there is a building right next to the barrier wall that's shown there as a gray bar. And they were very interested in knowing whether they had to do something to enhance ventilation in the building. What temperatures would they actually see? Would the floor get hot? And this is just a very simple simulation of that. And once we heat on the left side of the barrier wall, takes that up to boiling, over time, what's the heat distribution going to be? So that's another example of a numerical simulation for a very particular purpose, to answer a question. In this case, did we need to do ventilation? Do we need to do in some sub-slab cooling, for instance, or were the people in the building fine? And in this case, this indicates that they would be. The basis of all these calculations is keeping track of mass, and that's mostly water in this case, and then energy on the right, the energy fluxes. And you can see there are a lot of arrows here, and instead of pointing them all out, my point here is that it's not just energy in and how much does it take to make a site hot. It's how much is coming out, how much steam are you generating that is pulled out, and that's basically a heat removal. How much are you pumping to have hydraulic containment? That removes energy as well. Air being extracted has a little bit of heat in it, and then we have the heat losses. For small sites can be very dominant. To the bottom there's a loss of heat, to the sides as well. So we have to also predict those. And here's our big layer cake numerical model we do. We take a site and we slice it into as many as 9 layers, and typically it goes quite a bit deeper than where we're treating. As you can see on the left, the treatment interval at this particular site from 10 to 80 feet. We cut it up, and then we get the best available information for the properties for all these layers. And in the following slide here, there's an example of that on the left, the layer numbers, and their thicknesses, the estimated fluxes of water into these zones, and actually also we tell the model the predicted extraction rates if we're pumping from the different zones. And then we need to know porosity, initial water content or saturation, and of course ambient temperature. All of this is put into the model so that when we start simulating the heat, we have the right conditions. We have the right heat capacity for each of the zone layers. We have the right flow of water in and out of the layers, because that makes a big difference. So typical input on the left, I just show one example where we had to do a sensitivity study. There was uncertainty about the porosity, the actual porosity at a couple of layers. The starting water saturation can sometimes be a little tricky to estimate, especially if you're doing something to change it before you turn on the heat. In this case, we were going to pump the water down and then start heating. So the starting saturation was an uncertainty. So we ran some sensitivity studies. Flux of water, of course, is a typical uncertainty as well, and I'll show that in a moment. Then the model, we set up the model with different periods of heating where we vary the energy input. In this case, you see the percent ISTD power going up and down. And the output, as we talked about a little earlier, the upper is an energy balance from which we get the estimated kilowatt hours to be used. We get on the right side, we get the predicted temperatures for the different layers. You see also the temperatures in the brown, blue, and red. Those are the those are the bedrock layers below the target treatment zone in this case, and we wanted to know what temperatures were going to be achieved there because there was to be a deeper dewatering system, and we wanted to know what temperature that water would. And in the bottom graph here, the predicted saturation of the different layers. So basically, how much are the zones going to dry out, and what water saturation will you get to? That's another way also of predicting what fraction of a pore volume of water have you boiled and removed, and that's an expression of the steam stripping efficiency, or how much steam stripping you've actually generated with this heating. Once we have this model calibrated to where we think it's right, we can then look at these temperature profiles as we expect them to be. On the left, you see the base case where after about 150 days, the orange-brown line shows boiling temperatures from top to bottom above the dotted line, which is the bottom of the treatment zone. And we can then do sensitivity studies. We can vary different parameters and see if how badly it would hurt us if certain things happened. The middle graph shows, let's say we had 5 gallons per minute of upward flow from the bedrock up into the bottom of the treatment zone. We simulate that, and you see if that was to happen, it would be pretty bad for the bottom. Here we wouldn't reach boiling. At the bottom we would only reach maybe 80 or 90 Celsius. So that's a parameter that has to be controlled. We don't want to induce a very high upward gradient and this type of flow scenario, because if we did, we would end up with being too cold at the bottom, and that DNAPL down there would potentially not be vaporized. On the far right, another example, what if our vapor cover was uninsulated? What if we just allowed heat to basically run through the surface and air and ambient conditions to keep the topsoil reasonably cold or at ambient? What would happen here is that 50 centimeters down, 2 feet down, instead of being at boiling, you would be only at 80 degrees or 75 degrees Celsius, which is the perfect condition for DNAPL, PCE, TCE to condense out and then be left up there in the shallow zone rather than staying hot and being swept out with the extraction system. So again, this argues for, in this case, make sure the insulation value of the vapor cover is proper so that we don't get a cold top where we would have a buildup of contaminants. And one thing on the next slide here that is sometimes not very intuitive, but we need to boil somewhere between 10% and 30% of a pore volume to meet the goals typically. 10% would be for 111 TCA and sometimes TCE, some chemicals that are the more volatiles, and if you don't have a really stringent soil cleanup goal, you can get away with boiling 10% or that around that. Other sites, if there's strong sorption, contaminants with a little less volatility, like PCE, chlorobenzenes, you may have to boil as much as 30% of the pore volume. Once you take that into account, you can see here for an example site that if we just look at the pie chart down there, the energy it takes just to get to the target treatment temperature is only a little more than a quarter of the total energy to treat a site. The heat losses can be almost as big as that, and that's the green part of the pie chart there. And then the big thing is all the energy it takes to boil groundwater and make steam, and that steam flows out and carries the contaminants out. So if somebody not very experienced in this, just estimate the heat capacity and multiply it by the temperature rise you need, you'll underestimate the energy demand by a factor of 2 or 3. And that's a mistake that has been made in the past without naming it any names, but some sites have actually had really, really optimistic energy estimates, and and then it became apparent during operation that it was not enough energy to treat the site. You may be able to get close to the boiling point, but that's not enough to treat a site to the stringent goals. Another thing that's haunted us a little bit in the past has if we have inaccurate data or understanding of the groundwater regime and hydrogeology, and if we miss a zone where there's actually a substantial amount of groundwater flow, we can get in trouble. As you see here, I'm indicating with a model, red is 100 degrees, reaching the target treatment zone temperatures, which you can do in this case if there's only like 1 gallon per minute of water flow. Not a big deal. In this case, we're cooking enough groundwater to overcome 1 GPM, and we're extracting enough steam to have hydraulic containment. In the middle, with 5 gallons per minute flowing across, you start to see that on one side we're not reaching boiling because that water simply flows too quick for us to heat it up and reach temperatures there. And on the down gradient side to the right, you start to see some spreading of warm water down gradient. And that means, again, it's because we have more water flowing than we can boil off. And in this case, we're not simulating pumping, but that would be a remedy for this, to pump on the up gradient side. The more extreme case to the right, 10 gallons per minute, you got a big cool zone, and you're starting to have a thicker warm water plume, if you will, on the down gradient side. And that is equivalent to loss of hydraulic containment, and you would typically have thermocouples out there telling you, oops, this is starting to heat up, so now we have to do something. But this is definitely a non-ideal condition during, for instance, an ISTD project to have this happen. You need to predict it and prevent it. You don't want to observe it. Just going back to another energy balance, this is something we did for an ERH proposal. Just pointing out here that it is so important not just to look at the energy in and try to predict the energy demand and duration based on that. What you see here with the red arrows is kind of the size of the different energy streams. And as you can see here, with 17 going in, you can have, in this case, as much as 4.9 coming out, and these are megawatt hours cumulative over the duration of the project. So that's a little under a third of all the energy that's input is actually being extracted in hot groundwater, because when you're doing ERH like this and injecting water at the electrodes, you have to have hydraulic control and you have to extract it. And if you're doing it right and extracting a little bit more, not a whole lot more than what you're injecting, it's going to be really hot water, and it's going to carry quite a bit of energy out, and that has to be accounted for, as well as the steam that's extracted with the vapors, and then losses through the surface, the sides, and the bottom. So here is a table that focuses on TerraTherm's ISTD projects only, because it gets really muddy if we start to take also projects where we inject steam. The power doesn't only come from electricity, it also comes from gas that's being burned or diesel that's being burned. So I just focus this on ISTD projects that are similar for chlorinated VOCs. And it's a list of projects we've completed, and the farther down the list you go, the older they are. And we databased all of them, and with our predicted power usage, with whatever tool we had at the time, this was the amount of kilowatt hours we expected to use. And then I've listed the actual usage from monitoring at the sites. And under the variance of power use, the colorful column here, if it's red, we actually underestimated the amount of energy we needed. If it's not colored, we got really close. If it's green, we got either okay or slightly overestimated the energy. And luckily, what you see here when you go from the bottom to the top is that we have improved in our ability to estimate these things as we've developed all the models. We're more in the green zone now, or in the white, which means, you know, we don't have frequent exceedances where we're just using a lot more power than we expected. And the main things that we have learned, we've built better models, but we also are much more aware of the hydrogeology now. Almost all the projects that you see here in red, it was groundwater hurting us, and it was us not proactively stopping that groundwater from moving across the site. That's the #1 culprit for us early on, missing out a little bit on our estimates. So the first part of the presentation is almost over. The summary of that is, again, understand the site conceptual model. Of course, you pick the right treatment zone, so you encompass the zone that's above your target treatment goal. Once you do that and you know how it's going to be heated and how the chemicals are being extracted, you can have your design and you can do your predictive modeling. Don't forget the losses to the sides, to the bottom, to the top, and don't forget that you're pulling out energy. So when you're predicting an energy balance, you have to account for that. It's not just energy in. Then you do sensitivity studies for those site-specific things that are uncertain. Groundwater flux, quality of the vapor cover. You know, it's expensive to pour a vapor cover, so whether it's 6 inches thick or 12 inches thick makes a big difference. So you study those things and you find the optimum. Same thing we do with heater spacing. We can use 15-foot spacing. We can try to tell the model to do 12-foot spacing, then we heat much quicker, but we then compare and find the best cost optimum in there. And when you operate, of course, you have to watch for these things that can affect your final duration, and that's a whole different topic, but you got to really monitor the subsurface temperatures inside the treatment zone and down gradient to make sure you're not losing hydraulic control. The mass removal rate, so you follow what's coming out when you're starting to have diminishing returns, and then the water and energy balances, so you can calibrate to what your model was. And sometimes comparing depth profiles and energy balances really tells you if something is off and how to fix it. So just a few more slides. It doesn't always go as planned, as you saw in that little slide. We had 4 or 5 projects where we were at some point saying, hey, we're not going to be done exactly on time and we're going to need a little more juice, so who pays? So this has an impact on contracting. One of the more obvious things that can happen is what you see in this picture. We had a site where 4 feet of fill was placed on top and the original land surface was dry. Then a wet season hit, and it turned out that the original surface had been compacted quite a bit by equipment during the placement of this fill and before, and so we found water standing just a foot or so below the surface when we were ready to install these nice horizontal vapor collectors. They're supposed to be dry and easy to have under vacuum. So, for instance, this was kind of an unexpected site condition. So before we could start heating, we had to dewater and pull water out of the site, and that added somewhere around a month of extraction and groundwater treatment before we could turn the heat on. So little things like that you definitely need to capture. And this is another site that we actually did in 2007, where water moved from the right of the picture to the left of the picture at a much higher rate than expected. We went in and did some slop testing and hydrogeology assessment. We found out that the groundwater was moving at 30 times the pace that we had believed based on the data that was available before we did the design. So the hydraulic conductivity was actually 30 times higher than what we had in our database when we started. So at that site, it was a redevelopment project. We had to hurry up to find a solution. So we had to install a sheet pile wall up gradient, wrapping around this treatment zone. You can kind of see it on the right side of the picture. And then we had to install additional heaters in between the first heaters so that we could kind of catch up. But we had basically lessons learned was what I showed in the little model earlier on, and which you can see down below, flow from right to left. That's exactly how we learned that at this site, and it was painful, but we learned from it. Sometimes mass removal can be very difficult to predict. These are different cumulative curves for PCE sites we've done recently, and as you can see there, it's pretty obvious sites don't have the same amount of mass, of course, but it can be very hard based on soil and water data and spill records to know whether you're going to get 1,000 pounds, like you could do in the red line there, or 1,000 kilograms, or 5,000 kilograms, or as we expect at a site we're operating right now in New England, we expect up to 2 million pounds coming out. So we never can really estimate that mass very accurately. So for a lot of sites, there's an uncertainty associated with that, and the cost impact, of course, if you're using granular activated charcoal, it's more or less proportional to the mass extracted, and that's a variable we don't like to fix, and we'd like to keep it variable because it belongs kind of to the site uncertainty and not so much to the thermal company. So these uncertainties translate into options for how we contract, and this term guaranteed fixed price remediation is being used a lot. I just wanted to in this table show what, like an overview of the things that we can control and the things we can't so easily control, and with all-in guaranteed fixed price remediation in the middle column there, and then as you move right, more and more flexible contracting where we are only fixing the things that we can actually control. For instance, to drill, install, and construct the system that we have designed, that can easily be done with a fixed price and a guarantee that it works. Same thing to operate it based on the design and the modeled prediction, and put in the power, extract the fluids, treat the vapor and stuff with the system operating to specifications, collect all the data necessary. All that stuff can easily be fixed, and there's no discussion about the thermal vendor needs to do what they say and stick to it. And if something doesn't work, fix it. Then when it comes to running long or short, expanded or shorter durations because of mass or because of groundwater flow, those are the next rows down there. Those become pretty painful if we have to guarantee how long it takes and exactly how many kilowatt hours it takes, because we are now owning the accuracy of the estimates of starting water content, starting chemical mass, and what groundwater flow we will actually see when we start operating and pulling vapors and liquids out. So if it's an all-in guaranteed fixed price remediation, if we have to carry that uncertainty, as you see down below, I call it a cost premium. We have a high vendor exposure, and we could, for a $1 million project, have to add as much as $300,000 in contingency because we can't be sure, and we can't risk, underestimating some things. And on the far right, if we don't have ownership of those things, and if the client says, okay, it belongs to the site, it belongs to me, I own those uncertainties, then they pay a much lower price. And we only fix and guarantee those things that TerraTherm can control. Then instead of $1.3 million, maybe it's a $1 million project. And that's our preferred option. And it's typically also the option where the client pays the overall lowest price for the remedy. So in summary, we can predict how long it's going to take and how much energy it's going to take if we know the site, if we have the proper models, but there are always the uncertainties. Most of them are associated with groundwater flow or chemical mass to begin with, and exactly how long it takes to cook it, and how long it takes to get those confirmatory samples to satisfy the objectives. And what we do is the modeling. We conduct sensitivity studies, and the contracting point was, if the client accepts the responsibility for most of the uncertainties and contingencies, the overall price is the minimum it could be. So thank you so much for listening to me. I am now checking to see if I have questions that you guys have typed.